If I drop this ball, it's pretty hard to tell, even in slow motion, if it falls at constant velocity or if it speeds up during its fall. As you can see, it's very hard to tell if the ball is falling at constant velocity or if it accelerates. If Galileo's hypothesis was right, then from 5 centimeters it won't have any effect, but from 1 meter it's going to break the papers. This ball experiment, we know that this ball must be speeding up, but intuitively we can't see it with our own eyes. So, to make the ball fall slow enough for us to visualize this speeding up, we're going to have to use this inclined plane. If we're going to drop this ball at distances of 0.5 meters, 1 meter, 1.5 meters, and ultimately 2 meters. 1, 2.76. To find the velocity, the instantaneous velocity, which is why we have this extra 2, we're going to take 2 times the distance traveled totally over the total time traveled. 0.13 meters per second. 1, start. 3.74. 0.53. Human error, 0.14. Go. Two, 1, start. 4.88. First of all, you're probably wondering, why is our acceleration nowhere close to 9.8? It's a whole 2 orders of magnitude lower. Well, that's because we're on an inclined plane. You can do something like this to really raise the angle. And now objects are going to go on here much faster. 1, go. 3.33. You see the humongous difference just by raising the angle a little bit? If I place some bells at equal distances, they will start ringing at unequal intervals because the ball will go more faster over time. So it's going to sound like, and the final 2 are going to be very far apart. What I'm trying to do here is demonstrate that the time that it takes for this is 1 second. This is 1 second, this is 1 second. Find these using this formula that Galileo came up with. 0.075 t squared. 0.075 just by the tiniest margin. 187.5 or 1.875. 0.5 is right about here. Then 30 is right over here. You can see this gap is pretty small. This gap is a bit bigger. This gap is pretty huge. My dad.
Well, I'm his lab assistant. Okay.
Okay.
What do you want me to do?
So what he's going to do is, I'm going to drop this, and since I only have 2 hands, I can't be here dropping it, here at the stopwatch, and lapping everything all at the same time while making sounds. So, that's what I want you to do. 2, 1, go! This one is very close to 1, only 0.13 seconds off. This one is also very close to 1, even closer. This one is pretty close to 1. This one is a little far from 1, but still pretty close. And this one is basically exactly 1. Even though the distances increased quadratically, we still found that the time between each bell was the same. An object's distance from where it was dropped increases quadratically with respect to time. An object's velocity increases at a constant rate or linearly with respect to time. And an object's acceleration stays the same no matter what the time is.